Hello everyone. In the previous video we discussed what to do when we have resistances connected in parallel. We went ahead and discussed about finding the equivalent resistance as well as finding the current that goes through the resistances in parallel, the current division formula. I talked a little bit about what happens when you have two resistors, but I really wanted to create one dedicated video that covers the two resistors case because that's really a very common thing in real life. So I will very quickly repeat the results you've seen for the N case, but you will see that the equations we're going to get for the two resistors case, they're so, I would say, commonly employed and so intuitive that it's actually worth remembering them and not re-deriving them every single time. So this is the circuit I had shown you in the previous video. Imagine that you just have two of the resistances. So imagine that we only have basically R1 and R2. We have found out that the equivalent resistance, R equivalent, is related to the resistances R1 and R2 through this equation right here. So I can take this equation and I can find the R equivalent by just doing a little bit of algebra, and you will find out that R equivalent is equal to R1 times R2 over R1 plus R2. So this is the equation that you can use directly from now on to find the R equivalent for two resistances. It's basically the product of the two resistances divided by the sum. So don't have to always start from here. Just go ahead and apply this equation directly. The other formula we discussed about the case of parallel resistances is the current divisor formula. So again, imagine that you have just two resistances right here. Imagine that you have some current I that comes towards these two parallel resistors. The question is, what is I1 and what's I2? So just to remind you, I1 will be equal to the total amount of current that is flowing in times a ratio. And that ratio will be the conductance of the first resistance over the equivalent conductance for these two resistances. Or this will be equal to I G1 over G1 plus G2. The interesting thing here is that if you replace G1, which is the conductance of the first resistance, by 1 divided by R1, and then G2 also 1 divided by R2, and you do the algebra, you will find out that I1 is going to be equal to the current I that you want times R2 divided by R1 plus R2. In a very similar way, you can write down the second current. I2 will be equal to I R1 now over R1 plus R2. So in other words, this is going to be equal to the current I, which is the total amount of current that comes into the resistances, times the resistance you don't want over the sum of the resistances. So let me write it here with red color. So the current that you want, let's say I1, is equal to the total amount of current that you have times the resistance that you don't want. For the I1 case, this was R2. For the I2 case, this was R1, over the sum of the resistances. In this case, of course, is R1 plus R2. So keep that formula in mind, because even though you can always start from here, and that's perfectly fine, specifically if you know the conductances, but in the more common case, you actually know the resistances, not the conductances, and so you will save quite a bit of trouble just by remembering the one that I just showed you here. The current that you want is the total amount of current times the resistance that you don't want over the sum of the resistances. So I hope in this video I have summarized for you the two most important results that you need, which is the equivalent resistance of two parallel resistances and the current divisor formula for the two parallel resistances, so you can apply them and save yourself quite a bit of time. So thank you for watching this video. We will see you next time.